Hi, everyone. Welcome to day 3 of this great conference. This is breakout session 10A called Using the ACS to Measure Trends Over Time. I want to just briefly mention a very slight change to the schedule. This session is actually going to end at 11:37. And then the next one will start at 11:42, just to give people enough time to switch over to the different Zoom rooms. All right, so we have great speakers lined up today. The first up is Joel Alvarez, who is Deputy Director of Population Division at New York City Planning. And his presentation is titled The American Communities Survey's Place in 2020 and Beyond, an approach to reconciling small area ACS data with 2020 census geographies.
Okay, let me share my screen. And begin. Can I confirm? Diana, can I get a confirmation that you can hear me and I see everything all right?
Yeah, looks like it's in presentation mode, but we can hear you.
Then let me escape from this. Try that again. And
Looks good.
well, and now I'm really apologize for this. It's not looking out the way I wanted it to. Let me. Well, I went to the green room and tested this out, but it didn't work out quite the way I planned it. I apologize from this. But I will attempt to go back now to share screens with you guys. I'm so sorry for this technical difficulty. All right, can you share? Can you see now?
Yeah.
All right. And now here we are. All right, can you see everything all right again? And is it appears just as a presentation?
Yes.
As just this. Okay, thank you so much. Okay. Good morning. Thank you very much for that introduction. Sorry for the technical difficulties. Let me jump right in and begin by taking a break from all of the ACS discussions and talk about the 1990s, when we occasionally heard harrowing stories about Russia's Mir space station. In one incident witnessed by a guest American astronaut, a satellite actually crashed into the space station. Oxygen began leaking out into space, and a cosmonaut quickly sealed the compromised section with a spare hatch that just happened to be lying around. And on that coincidence, the vessel was pretty notorious for its accumulated junk. The Mir program was perpetually neglected in budget and high-level attention, but the cosmonauts always made do, employing basic ingenuity to overcome numerous hurdles. And importantly, they were always able to carry on with their core scientific research. And that's the approach I hope to offer here. Some cosmonaut can do in dealing with the geographic mismatch we're about to face this fall when attempting to examine change over time using the upcoming 2020 ACS that are due to be published in the new 2020 geographies. Right now, there's no officially endorsed solution. So we're gonna look around the shop and see what tricks we have lying around on the floor. And so that, like the Mir cosmonauts, we can carry on with our research. So first, I'm going to describe the challenge presented by this geographic mismatch, and then I'll describe our approach to reconcile ACS count estimates across changing geographies, followed by our approach to reconcile margins of error, and wrap up with some key takeaways. So first, the issue at hand. Here at the Department of City Planning, we have an online application for exploring population data called New York City Population Fact Finder. Starting with a map, users can choose one of New York City's nearly 200 neighborhood tabulation areas. These are approximations of neighborhoods built out of census tracts, or users can create a custom study area built out of tracts or other geographic building blocks. And we provide data from the tract level on up, but when we provide our tabular output, unreliable data are grayed out as a warning to users about the data limitations. What we found is that our neighborhood tabulation areas, or NTAs, typically provide pretty reliable results from the ACS output. So they're really our go-to geographies, while tract level data are pretty unreliable. This isn't that surprising given that tracts have an average population of about 4,000 people compared to our neighborhood tabulation area average of about 40,000. So along with the latest ACS data, we also show the ACS data, how the ACS data have changed over time using the 2006 to 2010 period estimates as our earliest timestamp. And this is where our challenge lies, because we depend on the tract data for our custom geographies and to construct our neighborhood tabulation areas. But about 6% of New York City's 2010 tracts are split in the new 2020 geographic release. So how can we convert data from our old 2010 census tracts if they're split into new 2020 tracts so that we can still examine change over time? We approach this problem in two parts. First, I'll explain our approach to reconciling our ACS count estimates across split tracts. So using that same example that I just flashed before you before, we're looking at a 2010 tract. We have 1,000 residents who worked from home based on the 2006 to 2010 ACS. Area-wise, the tract split in half, creating two new census tracts in 2010 or 2020. To distribute this work from home population to new tracts, we first examine the total population from the 2010 census. Next, we see how that total population is distributed at a block level. And then we use that block level population distribution to create a proportionate split between the two new tracts. And lastly, we use those proportions to distribute this subpopulation of workers who work from home to the new 2020 tracts. So to examine the impact of this approach, which is kind of a common approach, we selected 10 test variables that are used in New York City Population Fact Finder, but that are also available from the variance replicate tables so that we could eventually use them to assess our modeling of margins of error. These 10 variables ran the gamut. They cover demographic, social, economic, and housing topics. And we also needed these variables to be available at a block group level because since we don't yet have published ACS data in 2020 tracts, we used block groups in tracts that we knew to be split in 2020 as proxies for the new 2020 tracts. So with these 10 variables, we created modeled estimates and compared them to the published estimates for block groups that were in census tracts due to be split in 2020. And we calculated the absolute percent difference between the modeled and published values for each of these variables. And we found that there was considerable distortion at a block group level. The overall median absolute percent deviation was 37%, and all but two variables had median deviations of over 40%. However, most of you working with ACS data know that block group data are really noisy, especially when dealing with smaller subpopulations. The average block group estimate size for all of these variables was just over 100, So the numbers are really small, the underlying sample is small, and consequently, even the published estimates are unstable. So we don't expect these estimates to be that precise. And importantly, we don't intend to use them individually for our work in city government. As I said earlier, we use tract aggregations, or NTAs, when examining ACS data. Consequently, we examine the impact of modeled estimates in NTAs that incorporate these block groups in split tracts. So specifically, we looked at NTAs where such splits cross NTA boundaries to avoid splits that simply cancel out when we sum them up. And we had 37 such NTAs across New York. And the results at an NTA level look much better. The overall median absolute percent deviation for NTAs was 2.5%, and all but one variable had median deviations of under 4%. And this is really encouraging, and it's a level of distortion that we're comfortable with. While split tracts are spread out across the city, these NTAs that we analyzed had an abundance of splits. About a third of the component parts were split geographies with these modeled estimates. And even with this high proportion of split geographies, our analyzed NTAs still had reliable results. So at an NTA level, the distortion introduced by our modeling of ACS estimates is really minimal. So now that we have a sense of our approach to reconciling count estimates across decennial geographies and the reliability of those modeled estimates, now let me explain what we've done to reconcile margins of error across split tracts. So let's start by looking at the example I introduced earlier. Part of the answer to this question of reconciling margins of error lies in the proportion we used to create the split tract count estimate. When we look at that split tract count estimate as a percent of the original tract estimate, so in this example, 75%, we see a strong relationship between that percentage and the split tract margin of error as a percentage of the original tract margin of error. And you can see that strong relationship in this scatter plot. Here we used block groups as proxies for the new 2020 split tracts, and again use that work from home population, showing the count estimate percents on the x-axis and the margin of error percents on the y. You can see a clear positive relationship. It's not quite a linear relationship. It's a little more exponential. And when we apply a best fit exponential line, we get a very high R squared of 0.88. And so we were encouraged by this, and we explored this relationship for other test variables and got very similar results. So with this, we pursued a model that took all 10 variables into account, and we used the 2015 to 2019 ACS data variance replicate estimates because they permitted us to eventually create precise NTA margins of error for testing. And using this data set, we randomly selected 500 block groups from across the city and ensured that no two block groups were from the same census tract to help avoid covariance. And then we allocated equal numbers of these 500 to our 10 test variables. So 50 block groups for each individual test variable, and used the data to create a more comprehensive model. And the result was a good R squared of 0.81 and an ACS split tract margin of error equation. And this was really important. This was an equation that we could use to calculate margins of error in split tracts. So now, with this equation, we could plug in the percentage of the original tract count estimate allocated to this split tract, so 75% in this example, and get an estimate of the split tract margin of error as a percentage of the original tract margin of error, so 93% in this example. And then we just apply that margin of error percentage to the original margin of error and get a margin of error value for our split tract. And then it's just a matter of filling in the blanks. So in this example, we ended up with a margin of error of 93. So for the 10 test variables, we compared our modeled margins of error against the quote unquote actual margins of error calculated from the variance replicate tables. And again, looking at those 37 NTAs with boundary crossing split tracts, we found very reasonable and acceptable absolute percent differences. The overall median absolute percent difference was 5.4, and not one variable had a median difference in excess of 7%. Even more encouraging, we found that the majority of the error was attributable to our use of the generalized formula in aggregating up to the NTA level. And only a minority of the error was due to our modeling of margins of error for selected component geographies. Okay, so our key takeaways are that our proportionate splits of ACS count estimates produce reliable results for New York City tract aggregations called neighborhood tabulation areas, or NTAs. Our ACS split tract margin of error formula also produces reliable results at an NTA level. And both approaches have the advantage of being quite simple and easy to use. However, we do need to do further vetting on the impact of this approach. So we'd like to examine the distortions using other tract combinations. We'd like to examine the distortions looking at a few other variables that are available through the variance replicate tables. But that said, we're comfortable with the approach, but there are a few other alternatives that people could explore. Perhaps one could use the 2020 ACS data once published to similarly model splits, or perhaps someone could produce a more reliable multivariate approach for in estimating margins of error. Another alternative is to use what we used to call super tracts back in 2010. We use these or combinations of split tracts, essentially maintaining the old 2010 tracts, since it's easier to aggregate than to split ACS data. At a session yesterday, Michael Starsinik had a great creative suggestion that users could apply these proportionate splits to each of the 80 replicate variance estimates to produce an estimated margin of error for a split geography. And that's a great approach, but one we could not use because of the limited number of variables available and because of the variance replicate estimates tables don't go back to 2006 to 2010. Finally, the easiest route for all of us would be for the Bureau to republish old ACS data in 2020 geographies, but I have a sense that disclosure issues might preclude such a release. So yes, these alternatives could prove more effective, but for the time being, without such alternatives, we'll stick to our cosmonaut can-do approach and carry on with our core research. One last note, we don't have documentation posted on this yet, but we will publish detailed guidance on our New York City Population Fact Finder application once we implement this update. And thank you all very much for listening. Sorry for the technical difficulties. My thanks to the ACS Data Users Conference for hosting, and my thanks to the Census Bureau for continuing with this ACS program under such difficult circumstances.
Thank you so much, Joel. That was great. I loved the intro and the wrap up. Just a reminder for everyone, feel free to post your questions in the Q&A, and then you'll be able to upvote different questions that you'll see there. And when you do, feel free to write who your question is for as well. Our next speaker is Douglas Hilmer, who worked at the Census Bureau for 31 years. And since his retirement, he's been a contractor and a consultant on several projects using ACS data. His presentation today is titled, "Where Are Things Changing? Finding Trends in ACS Data."
Hi, thank you. And okay, I'm hoping
Looks great.
Can I be heard? Am I
Yeah.
okay?
Mhm.
This happened to me yesterday too. Uh, I mean, Tuesday. The slides seem to get ahead of me. All right. Yeah, where are things changing? And I'm going to tell you right away that I'm going to skip some slides in the interest of time. Um, but I have a paper that accompanies this talk, and it's much more detailed than the talk. So, real briefly, I'm going to cover 14 years of ACS data from 2006 to 2019. How can we use that data for historical analyses? Why I chose education attainment as the topic to investigate, and um, why I chose counties as my geography, why I chose to use a single ACS table as my data source, how I chose to measure change, what I found, and what I learned. Um, so why use the 1 year data, which is what I did? Well, obviously, it gives me 14 data points. The 5 year data would only give me 2 right now, even adding the most recent 5 year data later this year would only give me 3 data points. Um, the 5 year data has another drawback, and that is that it's sometimes very difficult to see a trend when you are looking at 5 year data because it has a kind of smoothing effect which masks out what might be going on. The 1 year data is very timely, but it has a couple problems too. Of course, we know the population threshold is 65,000 or greater. That's one of the issues. The other issue is that in contrast to the 5 year data, where there is no data quality filtering, there is data quality filtering applied to the 1 year estimates. And that can have anything from a minimal effect to a very large effect on the population subgroup that you want to study. So I decided though that the 1 year was a better one if you want to look at trends. So that's what I'm doing. Why did I choose educational attainment? Well, I will skip some of the background here. Um, Basically, educational attainment is well studied at national and state levels. And I wanted to have some benchmarks, which I do have. And by the way, the paper has an appendix that covers some of the references. Um, so I just went with 2 measures at 2 extremes: no high school completion, including GED, and bachelor's degree or higher. And then what I did is I decided to disaggregate further. I wanted them by gender, and I took and then 3 major race groups, or 2 race groups: white alone, black alone, and then Hispanic origin. When I was all done, I got 24 separate measures that includes 8 measures that are ratios of men to women, in, either with the relation to the bachelor's degree or higher, or no high school graduation. Um, it's a lot of measures, but um, that's what I wanted to look at. So why did I choose counties? Well, and there are a lot of other choices, but counties are known to people, and they have local governments. Um, People not only know their own county, they know nearby counties. Um, the other big advantage of counties is their boundaries change very infrequently, and they are not subjected to census boundaries. In other words, they are not a statistical geography, they're a political geography. Pumas have advantages, and I did consider Pumas. The biggest advantage is you get what I would call wall-to-wall coverage. In other words, the entire country is partitioned into Pumas. Um, However, because they are so close to the 65,000 population threshold, remember the average size of a Puma is about 100,000. They are they are very much affected by data quality filtering, the suppression from data quality filtering. So I shied away from Pumas. Also, of course, right in the middle of my time period, the census happens, and that meant the Puma definitions changed. I also looked at cities. They are good alternatives, except for the fact that their boundaries change much more frequently. I chose to use one ACS table as my source, and I tried to get the best fit, meaning I wanted the smallest table that still had enough detail so I could actually calculate my measures. And fortunately, what they call the collapsed version of the bigger table, the C table, is there at C15002 and its iterations. And I recommend that in general, always try to find the smallest table that covers what you need because obviously it's less subjected to data quality filtering. That probably isn't too easy to see. That's simply the template for the table, and you can it has more than I need actually, but that's still less than in the full table. These are my processing steps. They're very straightforward. Everything was done directly with the API. I calculated all of the margins of errors that I needed in my measures, although you'll see later I didn't really use them directly. I created the reports. I created graphs. All the programs are written in Python. Okay, well that brings me to an example of a result. And I want to just spend maybe a little more time on this slide because this is a slide from Rapide Parish, Louisiana. And I think anybody looking at it would say, well, yeah, there does seem to be a downward trend. And that's good because it's the measure is no high school completion for Black females 25 and older. However, one thing to point out is that there is none of the year-to-year changes is statistically significant at the 90% level. But intuitively, we seem to think, yeah, that would be a trend. And that is an important factor, I think, when you're looking over a long period of time. So you can't just depend on test significance. So I decided I needed to do something else. So I decided to use a non-parametric test called the ManKendall Test. It's a trend test. It is I've never found an application in social sciences. It's mostly used for weather-related hydrology applications. However, it has an actual very sound hypothesis testing capability. And I'm aware of a trend test based on regression. It was not exactly clear to me how to use that. And the ManKendall test just struck me as more straightforward. So that's what I decided to use. Okay, the basic measure is called S, and you can see it's based on a double summation, but it's pretty simple. So you go from left to right, from the beginning year to the ending year. This is the inner sum. And you calculate not the differences themselves, but the sign of the differences. In other words, if it's a positive difference, it's 1. If they're the same, it's 0. If it's a negative difference, it's -1. And you add those all up. Then you move your left-hand side 1 year forward and you repeat this. So with the 14-year period, it turns out that the interval is going to be between -91 and 91 for S. And you notice that a consistently upward curve would get close to 91 and a consistently downward curve would get closer to -91. Notice that this is about consistency, not about magnitude of change. So this does allow for hypothesis tests. It can be carried out at any predefined confidence level using a p-value. A test statistic, a kind of z statistic, is created by the ManKendall approach, and it's tested to see if the value returned is less than the predefined p-value. If a trend is determined to exist and the direction of the trend is the direction of the trend, upward or downward, is determined by the S value. It could be positive or negative. If that doesn't happen, a null hypothesis not rejected and no trend is reported. And you'll notice my p-value is set pretty low. That's a 99.9% confidence level. So what I found? Well, I found that the total population that I could study was in 817 counties because I wanted to have at least 10 years of results. And so some of the counties didn't have 10, I had to discard them. The Black population was hit pretty hard by data quality filtering. I could only see out of those 817, 489 counties. Similarly, for the Hispanic population, I could only see 513 counties. However, for whites, blacks, and Hispanics, for each group, over 80% of the population of that group was covered by these counties. So here's a summary. Both decreasing and increasing trends, you see them there. And together they make up less than 10% of the total number that were tested. Almost 17,800 were tested, and just under 10% of them showed trends. And this table is a more detailed report on the same thing. I'm certainly not going to go through this in any detail, but I do want to point out one thing. For both bachelor's upward trends and the high school non-completion of high school downward trends, the females for all subgroups are outpacing the males. They're improving more than the males are, and you can look at this in detail and you'll see that. And that is very consistent with what is already known nationally. Now, I'm going to skip these next two slides. I'm just going to say a little bit in the findings about these. This is the metro parts of the state versus the non-metro parts of the states. But I'm going to skip them for now. And I'm going to go directly to findings. So my results are consistent with results, both measures at the state and national level. A limitation for high school completion results. You may have noticed, or maybe I forgot to say this, that table C15002 and its iterations is based on the population 25 years and older, which is standard for educational attainment tables from the Census Bureau. However, that can mean that you cannot attribute a downward trend, in other words, more people are completing high school, to some policy or program implemented by the school system or the county. It could be due to something as simple as migration that happens. In other words, you graduate when you're 18, and then we don't start measuring this until people are 25 or older. Another thing, I would like to see if I could disaggregate by age, but then I'm obviously face the problem of even more reduced statistical quality. I've done quite a bit of disaggregation already. So I may have to do that at a higher geographic level. I'm still thinking about that one. Or there may be a way to do it with some other like Pumas or something else. Now, the no trend results in the non-metro areas versus the metro areas. Well, there's a lot more sample from the metro areas. They're much larger. So in other words, the metro portion of a state has a lot, and almost every state has a lot more than the non-metro portion. So there is more sampling error. However, they are striking results, and I think it's something that merits further study. Speaking of striking results, these are two that caught my eye. These are for Baltimore City. For Black alone population, men and women not completing high school. And you can see where they're starting from, especially the men, over 30% were not completing high school. And it's a rather dramatic drop. I was able to contact someone in Baltimore Metropolitan Council government, and he is right now analyzing this. Take a look, he was interested in it. And I've also not just sent him the graphs, I've sent him all the data that I used and the measures themselves. So what I learned and what I would do in my next project. Well, one of the things is, can I use pre-aggregated data at the Puma level to get better coverage? That would be helpful as long as I don't get hit by too much data quality filtering suppression. Is there a single table in the ACS data products that supports what I want to measure and does not change throughout the time period? By the way, it is important that does not change throughout the time period. Unfortunately, there are tables that have the same ID throughout the time period, but they are not the same table. So you have to be careful. And the ACS office has done a great job of showing all of the templates for all the tables every year in full production. Is there a way? Oh, if I can't use this table, can I create this from POEM's microdata? Is there a way for me to check my results against some already created data product, perhaps margins of a table or at a higher geographic level? Of course, you want to do that to get some reassurance that things are looking the way you might hope they would look. Should I use the 1 year, or would I eventually be able to use the non-overlapping 5-year periods? Well, I think we have to wait quite a while if we're looking at trend analysis. And as I said, we have to be careful about that smoothing effect. There's an example given in the paper on that. Is the population subgroup I want to study fairly evenly distributed across geography, or is it distributed in a skewed manner, as is the case with the Black alone population? This is a map I made. I'm a Social Explorer user, and this is a map I made from Social Explorer, thematic map, median income, median household income, and you see the markers indicating where trends were measured, and the pink ones means there was a trend. There's a detail for Western Pennsylvania and Eastern Ohio. Thank you.
Thank you so much. Great work. I do see one question about will people be sharing their slides? And I just want to remind everyone that the slides are available at the bottom of this session page under session content. And then we did have one kind of a two-part question from Matthew for Joel about thanks for the great info. For the race iteration tables, we could probably get estimates for 2020 geographies using race-specific 2010 block data. But is there anything you can recommend for MOEs since race iterations are not in the VREs? And then secondly, anything you can recommend for refining estimates in areas where the distribution of the population within tracts has changed since 2010, for example, new housing units?
Okay, can you hear me all right?
Mm-hmm.
Okay. So for the first question, let me think about the race iteration table. So yes, we only use the variance replicate estimates for our testing to see whether or not the modeling was effective and reliable. And so one thing that you can do in our approach, the modeled margins of error are dependent on those estimate proportions that are also modeled. And so if you wanted a model that was more for margins of error that was more effective, you wanted to be more precise, you wanted to get greater reliability in those margins of error for race data, then you could have rather than this generalized approach that we used for the proportionate splits based on the overall population, you could create specific proportionate splits based on race. So that could be an alternative approach that would probably increase the reliability of these modeled margins of error for race groups. And then could you repeat the second question?
Sure. Anything you can recommend for refining estimates in areas where the distribution of the population within tracts has changed since 2010, for example, new housing units?
Yeah, for our approach, we were looking at data from our earliest time point, 2006 to 2010. So that population distribution from 2010 was great. But if you are attempting to create equivalence between more recent data and the soon to be released 2020 ACS data, then perhaps you could turn to administrative data for your proportionate splits. So you could look at you could look at instead the latest housing statistics at a block level to create the proportionate splits, and that would probably do a better job of addressing these. If you have an area with a great deal of development, that'll do a better job of approximating the splits.
Thanks so much.
Mhm.
I don't think we're going to be able to get to all these questions, but I do want to give Doug one question that came in very, very quickly because I know we're over time. I have seen some research that the high percentage of Black men without high school diplomas in prisons has important implications for attainment measures. Did you look at counties with prisons in particular?
No, and I have a lot more to do on this. I mean, I didn't go into any of the specific characteristics of the counties I measured, and so I could certainly look at that. But there's a lot of other things I would want to look at. Basically, I made no attempt to come up with explanatory variables. In other words, I made no. This was just where are things changing, and it's only meant to be like this is the beginning. But it's a good idea. I'm making a note of that. That's one thing to look at. Thank you.
Thank you. Thank you all so much. And I know this was a short session, and I just want to say thanks everyone for joining. See
Okay.
you later.
Bye
Thank you.
bye.
Bye.
Thank you very much for hosting.
Thanks. Yeah, thanks for hosting.